In this video, we will learn how to preprocess our data in Python. Preprocessing is a very important step in almost every machine learning pipeline. It turns our raw data that is, for us and also for the model, hard to work with, into data that we can use to effectively train our machine learning algorithms. We can divide preprocessing into data engineering and feature engineering. Data engineering, as the name suggests, is the job of the data engineer. And this job starts at the very moment the data is measured. When the data is measured, it's in a very raw form, and it might be split across multiple datasets or files. And so one part of the data engineering process is to merge different datasets together and possibly also format them such that in the end we have, for example, a nicely formatted CSV file. When the data is measured, it might happen that some error occurs and the measurement becomes invalid. This would then require some system to either remove these invalid measurements or mark them in some way such that we can properly deal with them later. Now onto the second part of preprocessing, which is feature engineering. This is the process of using domain knowledge to transform our existing features and also to create new features. And we're doing all that with the goal to optimize the learning of our machine learning algorithms. Note that there's not a hard line between data engineering and feature engineering, because we could, for example, argue that dropping features is also a way of engineering them. And another example is dealing with invalid measurements. From the data engineering perspective, we might mark these values as 0, for example, to indicate that they're missing or invalid. And then in the feature engineering step, we might again deal with these missing values, but this time we're not simply replacing them with 0, but we could impute them with the mean or a predicted value. Okay, so the plan for this notebook will be to preprocess a dataset, and in doing so show how the various preprocessing steps affect model performance. The data that our model will be training on is taken from the Zomato dataset, which is a collection of restaurant data, also including the rating of the restaurants, and this rating is what our model will try to predict. Here we can see an overview of the different steps we're going to take. First up, we'll need some imports and change some settings. Then we will load the Zomato dataset. Then we will write a function to train and evaluate our model so that we can then run this evaluation after the different preprocessing steps to see if they have an effect and if that effect is positive or maybe even negative. Now, as for the preprocessing steps, we will start with data engineering, where we go through a couple of feature selection methods, and then right after we jump immediately into the feature engineering, where we will first deal with missing values, then encode the nominal variables, then apply feature scaling, and then jump back to missing values, this time with some more elaborate techniques such as neural network imputation and KNN imputation. And the reason this part comes up here is because these techniques, so the neural network and the k-nearest neighbor, work better with scaled features, and they require numerical values, which we only have after encoding the nominal variables. Now, starting off with our dataset, let's briefly check out some of the features to see what we're working with. And in the first column we have the URL of the restaurant, which will probably not be that important for us. Next up is the address, which might have some importance. Then the name, which is probably also not important since it's a unique feature. Then online order, which might be important, same as booking table, so whether or not at the time that this data pointer was recorded, it was possible to book a table. And then our target feature, the rating, then votes, so how many people rated the restaurant, phone number, probably not important, location, this relates to the address, so we might drop one of them. Then we have restaurant type, and we can already see this kind of relates to the cuisines column. So for example, here in this data point, we have both cafe here and coffee also here, so we might be able to combine these two features somehow. Next up is dishes liked, which can also be of importance. Then the cost, which is definitely important. The reviews list. This could be a very important feature, but it's also very hard to process, which is also why we skip it in this video. Next up is the menu of the restaurant, and we can see there's a lot of missing values in here. So although it could be important, we might drop it if there's too many missing values. Next up is the type of restaurant, and this is very similar to this restaurant type column, so we might also find some overlap or just drop one of them. The same applies also for listed in city, which is basically the same as location. And then we also have a cost in euro. So before we had another cost feature, which is in some other currency, and so it will definitely make sense to drop one of them. Okay, now onto our model and the model evaluation. Our model is a simple neural network that we took from scikit-learn and that we can use to do regression. So the rating that we will predict later will not be a categorical variable, which is also possible. We could have the categories 0 out of 5, 1 out of 5, and even 1.5 out of 5. But since we have more fine-grained values, like 3.7 out of 5, we might as well use them and then do regression. To walk you through the codes, we're passing the data frame to the model train and evaluation function, and also the target that we want to predict. And then our features are the whole data frame minus, so we're dropping the target, in this case the rating. And then our target is the data frame where we select the target. Then we initialize our MLP, so the multi-layer perceptron or neural network, and we have 3 hidden layers. We use the ReLU activation function, the Atom optimizer, and a learning rate of 0.01. With our features and targets and the model, we then run a 5-fold cross-validation, and from this cross-validation, we extract the test scores for each fold. We calculate the mean from that, and that is then our evaluation metric by which we judge our model, and then also the effect of the different preprocessing steps. Okay, so now let's start with the actual preprocessing. And our first step will be the feature selection. But before we start, it's worth asking the question, why do we even bother to select features? Because doing so does not give the model any extra information. And so after all, an ideal model would just select the important features and then learn from them. So assuming we have a perfect or ideal model and also enough samples, then there would be no reason to perform any feature selection. And doing so might even harm the process. But of course, you might be already thinking, is there really a perfect model and when do we ever have enough samples? And so given the obvious answer to that, it does make sense to perform feature selection and in doing so, make the job of our model easier and thus acknowledging that it's not perfect and probably it will not get enough samples. So it makes sense to help the model where we can. Now, how does selecting features make the job of the model easier? First off, by removing features that are redundant or irrelevant, we're taking one task away from the model, which is to learn that these features are not important. And so if the model does not have to learn this, then it can converge faster and possibly also converge to a better optimum, because it does not have to bother with the redundant or irrelevant features, which are essentially just noise. And at the same time, this also then speeds up the training time and uses less resources in terms of computing power and memory. Another advantage is that removing the irrelevant or unnecessary features also counteracts the curse of dimensionality. And then finally, if we have fewer features, it becomes easier to interpret and visualize our results. Okay, so how do we select features? And we will do this in 5 steps. First, we will remove the obviously irrelevant features, then we'll remove features based on their percentage of missing values, then based on the amount of variation, then pairwise correlation, and then you'll get some resources for other methods. Because feature selection itself is a huge topic, and there's, as you would expect, no single best way of performing it, but instead it differs from dataset to dataset, and especially from model to model. So let's look again at our features. And then we ask which of these features are obviously irrelevant. And the features that come to mind are the URL, the address, the name, and the phone number. And the reason they're not relevant is because they're unique. So there's no pattern that the model could extract from these features. Arguably, the address also contains information that is not unique, such as the general area that the restaurant is placed in, but this information is also contained in the location feature. So then address becomes irrelevant. And we drop these features by calling on our data frame the .drop and then pass the features as a list to the columns parameter. Next step is the percentage of missing values. And if we have a feature that has, let's say, half of the values missing, then it can make sense to just drop that feature altogether. However, it's also possible to turn the missingness of a feature into a feature itself. And then the model might learn from the fact that a feature is missing or not. To give you a concrete example, we could think of some measurements of some machine in some factory, and it might happen that whenever the temperature exceeds a certain limit, the sensor does not record anymore and produces missing values. And so then this feature of temperature that's missing half of the time can still be an indication of whether a certain temperature is exceeded. But we will not handle this in this section, but in the designated missing value section. Okay, next step is the amount of variation. If a feature varies very little, then we can argue that it contains very little information and thus will not be relevant to the model's learning. In our case, up to this point, we have very few numerical values, And out of these numerical values, none have significantly low variance. So in our example, we're not dropping anything based on the amount of variation. Our next criteria for feature selection is the pairwise correlation. And this helps us to drop redundant features. And so the idea is if two features are highly correlated, we can drop one of them, because one implicitly also carries the information of the other. And of course, this only works for our numerical features, which are so far votes, the approximate cost for two people, and then the cost in euros. But still we can see that besides the features correlating with themselves, which are the squares here, here, and here, we can also see these squares here and here, which is the correlation between the cost in euro and the cost in some other currency. And these features are obviously correlated. And if we check this scale here, they actually have a correlation of 1, so they're perfectly correlated. And in this case, it makes sense to drop one of them. Here we're dropping the cost in the other currency. Another feature that is highly correlated, which we saw before, is the location and then the city the restaurant is listed in. And location is more specific than the city, but since the location has too many unique values, we decide to drop it. We also apply the same idea to the restaurant type and the type the restaurant is listed in, which are again two columns that are heavily correlated. And in our case, we keep the restaurant type column because it has more restaurant types. If the correlation between alphabetical features is not obvious, we could use some NLP, for example n-grams, to check if and then how much they are correlated. Okay, then as for other methods. As previously mentioned, feature selection is a huge topic, and you can check out some more information with this link here. But in general, you should be careful when applying more complex methods, because it might happen that the time spent for feature selection is not warranted by the time saved during training. So it can pay off to do simple things, and it always pays off to make sure that what you're doing actually works. So the most advanced feature selection technique might actually reduce performance in your specific case. And it's also good advice to stick with established code, for example from scikit-learn, which is also linked here, because you can make sure that that code works and you're not wasting too much time coming up with your own code that then might also contain some bugs. Okay, finally, as also teased in the beginning, we will do some more dropping. Namely, we're dropping the reviews list feature and the menu of the restaurant, because these are very complex language features that we don't want to process in here. That being said, they might carry very relevant information, and it could be possible, for example, to apply sentiment analysis to the reviews and then use that result as a feature. Okay, then next step is feature engineering. And our first step here will be to deal with missing values. And to deal with them, we have several options. Namely, simply dropping them, then imputing them, so replacing the missing value with some other value, or as also mentioned before, we can turn the missingness of a feature into a feature itself. And again, there's the question, what is the best approach? And there's a review that covered 197 articles that applied different imputation methods, and they came to the conclusion that there's no single best method that always works. And instead, the performance of the imputation methods always depended on multiple factors, such as the feature selection, outlier detection, feature normalization, the classifiers, so the models used, and also the field of application. And so for our example, when we're not dropping the features altogether, or turning them into a feature, we will use two very common imputation methods, which are k-nearest neighbor imputation and ANN, so artificial neural network imputation. And then we'll see what works best, at least for our example. And so let's check first in which columns, so for which features we have missing values and how many. And we can start off with the rate column, and we can check the unique values in that column. And we see some are not a number, so they're missing. Some have the string new, and some also have this dash. And so since this is our target variable, it makes sense to simply drop the data points where this target is missing, since our model will not be able to learn from that. So we specify we want to drop the nans, the new, and dashes, and then we only select from our data frame those rows where the value of the rating is not in this list of criterias. And so now we only have proper ratings. The next column is the restaurant type, where we have 227 missing values. And because we're dealing with categories here, it can make sense to turn the missing values into its own category. And so what we'll do here is that we create the category undefined. And then we take our data frame and we fill the NAs, so the not available values, in the column restaurant type with the string undefined. So that's not our new category, and so we can see now it's not missing, but it's undefined. Next up is the dish liked column. And this feature is missing for almost 46% of the restaurants. And in this case, it makes sense to turn the missingness of the feature into a feature itself. So we create a new column called has liked dishes, and to there we assign whether or not the dish liked is missing or not. And the dish liked column, which you don't need anymore, gets dropped. And so now the has liked dishes column is a Boolean feature that indicates whether or not the restaurant had a dish liked associated with them. Okay, next up is cuisines. And we can check how many missing values there are for this feature. And luckily there's only 11 missing. So in 11 rows there's no cuisines. And for us that means it's not worth considering, and we can just drop these rows, because in doing so we'll not lose that much information. And now for the final feature that has missing values, we have the cost in euros. And for this we could apply something very simple, like taking the mean or median and then filling that into the missing spots. But we can also apply the more advanced techniques, which are the k-nearest neighbor imputation and the artificial neural network imputation. However, we cannot do that yet because we need our datasets to be fully numerical and in the best case also normalized. So before we come to that, we have to apply some other preprocessing steps, which takes care of these nominal variables. And we can check which of our variables are nominal variables. And we can see it's the online order, booked table, the rating, restaurant type, cuisines, and city. And we'll start with the online order and book table. And you can see both of these features have values that are either yes or no. And these binary variables we can simply encode as booleans. So that means the yes gets mapped to true and the no gets mapped to false. And we apply that 2 times, first to the online order column and then to the booked table column. And so now if we check these features, we have true and false. Next, we take care of the rating column. And here we're dealing with strings of fractions. And to turn them into floats, so numerical values, we can simply remove the /5 and then cast the remaining part to a float. So for every x in our column, we replace the /5 with an empty string, leaving then just this value in front here, and then we cast that to a float, and that gives us then floats. Next up is the restaurant type. And in this column we have 88 different categories. And a very simple approach would be to directly one-hot encode the whole column. So this would look something like this, where we now have 88 new columns, and the value in a row will be 1 or it will be hot only for the according restaurant type. So currently everything's 0. Let's remove the head function. And then we can see at the end we have a 1 in here, meaning that for this row, for this restaurant, the restaurant type was bar. And while this could work fine, the problem is 88 features is a lot considering that most of the values are 0. So this would give the model very sparse information, which we generally don't want. And so what we can do is that looking at the different restaurant types, we see that there's some overlap. So for example, this restaurant type is considered bakery and cafe, or here we have bar and pub, or bar and lounge. And so for example, bar appears multiple times. So instead of simply one-hot encoding the features, we can first split these different restaurant types into the unique building blocks, such as bar or bakery, and then for the different restaurants, we can place a 1 for the unique restaurant types that apply. So if it's a bakery and a bar, we can have, for example, a 1 here and also a 1 here. And the first step towards that is getting the unique types. So we can see here, now it's not bar and cafe or bar and casual dining, but they're all split. And now the cool thing is that this way we reduce the number of categories to 25. And now the only thing left to do is match the type of a restaurant with these categories. So for every single of these unique types, we create a new column, and if the restaurant type of a restaurant contains one of these types, the value placed in that column will evaluate to true. So we run that, and we can see that these first ones are of the type casual dining, and let's slide the data frame a little bit to the left. And now we can see the third restaurant is both a cafe and also a casual dining place. So now if we again go to the head of the data frame, we can see we only have 34 columns, and the new columns we added are also less sparse. And with that we can also drop the original restaurant type column. Next up is the cuisines column. and in this column we have 2,383 different categories, which is quite a lot. But again, looking at the column, we can see that there is some overlap. So for example, we have fast food here and also fast food here, although so far we would consider that as a unique value and that as a unique value. So we apply the same technique as we did for the restaurant types, where we first split the different cuisines into their atomic parts, and then we check as we create new columns for every category if the cuisine of that column is contained in the restaurant's cuisines. So basically if the restaurant offers that kind of food. And so now we have a column for pizza, coffee, and so on. And we had to add a C at the end of each category because otherwise there could have been some overlap with the restaurant type. So for example, coffee is pretty close, and there might be the food type bakery food in here, as we can see here actually. And so for it to not overlap with the restaurant type, we add the C at the end. And then again, we can drop the cuisines column because now we have the according numerical feature. Next up is the city, and here we're not dealing with that many unique categories, meaning we can simply one-hot encode this feature. And the one-hot encoding is done with the get dummies, and to that we simply pass the according column, and this gives us then this new data frame, which we then simply concatenate with our original data frame. So that was our original data frame, and this is the new one-hot encoding for the cities, and we can see that in here. And so now we can check with the function isNumericDType if all our features are numeric, and indeed they are. And now with all our features being numeric, we can finally start evaluating the model. Okay, the model is done training, and as a small reminder, we're checking the mean test score after running a 5-fold cross-validation. And our test score here is 0.38. For the kind of scoring we're using, the higher the score, the better the model is. And so this value is okay, but not really good. So what we can do next is we apply feature scaling. And the idea behind feature scaling is that each feature should have equal importance. And so imagine we have the features age and height, and the values for age might be between 0.0 and 100.0. So 0 years and 100 years, and then the height might have values between 1.0 and 2.0, so 1 meters and 2 meters. And without any scaling, the model will think that age has a greater effect on the prediction than height, because the values go up to 100 and here the values only go up to 2. And so to prevent it, the feature scaling method that we will apply is standardization, which ensures that our features have a zero mean and a unit variance. For that, we will import the standard scaler from scikit-learn preprocessing. We select the integers and floats of our data frame, because of course only to them we can apply scaling. In theory, we could also scale booleans if we imagine them as 0 and 1, but this does not really make sense and sometimes can also be harmful. So we select these columns, we initialize our standard scaler, we fit the scaler on our numerical columns, and then transform the columns. And now we can evaluate our model again, and then compare it to the base score. And as we can see, our model performance actually increased significantly. So we went from 0.38 to 0.53, and all that just by scaling the features, which is a very simple thing to do. Next step is the second part of dealing with the missing values. We left off at the cost feature, where we said we could use the mean or the median, but we want to employ some more advanced techniques such as the KNN imputation or the artificial neural network imputation. And we can see we have 244 missing values for this feature. And so for both techniques, we will copy the original dataset such that we can impute the missing values for both techniques into the respective new data frames. And the first step for the artificial neural network imputation will be to select those rows where the cost is not missing. So here we can see in the cost column, we have values for each of the restaurants. And then we simply train a neural network on these rows where the cost is not missing. So this data frame of cost not missing rows is passed to our training function, and in there we drop again the target, which is this time the cost. So that's the thing we want to predict, so impute later. And we also drop the rate because that's our original target, and if we don't drop that, then our model could cheat because it might implicitly get also information from the rate feature. And so then we have our MLP here, we train it again with cross-validation, and then return the results. And the results we get contain a lot of things, such as the time it took to fit the model, the different estimators for the different folds, the tests and train scores. And what we will do is just simply select the first model. So from the result dictionary, we take the estimator and then take the first estimator, so the first model. And then now this time we take not the rows that have the cost, but we take the rows where the cost is missing. So out of our data frame, we select those rows where the cost in euros is null. And then this is our input to the model, so the rows where the cost is missing, and we use that to predict the cost of these rows. And then we simply take the predicted cost and use them to override the missing values. It is important to note that what we're overriding is not the original data set yet, but just the subpart where the cost is missing. So this is the data frame with the rows where the cost is missing. So without this part, we have all the columns, but just the 245 rows. And then we access the cost column where there's only missing values. And then this, which is that part here, is then overwritten with the predicted cost. So when we run that, we can check again. And now we have our predicted values in here. And of course also in the subset of the data set. And so now we can simply merge this data frame with the original data frame. And so on our original data frame, we access the column cost in euro, and then we call combine with the column of the predicted values. And we run that, and now we have imputed all the missing values in the cost column. So then we can evaluate our model again, and then we compare the base score with the feature scale score and the ANN imputed score, which of course also has the feature scaling. And as we can see, the imputation with the neural network improved our score. So we went up from 0.53 to 0.54. And then in comparison, we can also try the KNN imputation. For that, we copy again the original data frame, we initialize a KNN imputer, we fit that imputer on our whole data frame, and then with the imputer, transform the data frame such that our missing values get imputed. And then we again evaluate, and this time we can see the score actually got lower. So we ended up with only 0.51, which is significantly lower than the neural network imputation, and more importantly, even lower than the score without any imputation. And this highlights again the importance of setting up the model evaluation first and then always checking if the things that you're applying to your data actually work or if they make the model perform worse. And then finally, one step of preprocessing can also be the removal of outliers. We will not deal with that in this video, but you can find some resources linked here.